Okay, so this is the second video on laws of exponents that we want to cover today. And we're going to pick up on the last three rules or properties using the laws of exponents. The first one uses a concept similar to what we already used before. And let me demonstrate an example. It's incorporating the power to a power rule. What you see here, and what's a little bit different, is I have two different bases inside the parentheses that are being raised to this power. And if I were to work this out in long form, which is not desirable, this is what I would be doing. Well, if I simplified all of this, you would see that I would get 81a to the fourth power. Well, I don't want to, because we've said this before, we don't want to have to write out multiplication number of times. So the key difference here from what we talked about before and what our rule number 4 is telling us is if we have more than one base inside this parentheses, we distribute the exponent to each base. So rule 4, which is called power of a product or quotient, tells us algebraically, if I have a times b to the m power, that's a to the m and b to the m. Or if I have a divided by b to the m power, I'm sorry for that not so nice looking m, that it's a to the m divided by b to the m. So in words, what we're saying is if more than one base is being raised to a power, then distribute the exponent to each base. So let's demonstrate this with a couple of examples. If I had negative 4 x to the third to the fifth power, okay? Or let me change that around to make the numbers a little bit more workable. Negative 4x to the fifth to the third power. What that is telling me is to distribute the 3 to the exponents of negative 4 into 5. Well, as we've learned, if there's no exponent written over a numerical base, it's an exponent of 1. So that means negative 4 to the third, x to the 15th, which means negative 4 times itself 3 times, which gives you a negative 64. As another example, if I had 3x over y to the fifth, all raised to the fourth power, this exponent of 4 would be distributed to all 3 of the bases to get 3 to the fourth, x to the fourth, y to the 20th, which we would simplify as 81 x to the fourth, y to the 20th. The most common mistake that students make is to forget to distribute the exponent to the numerical base, or forget to distribute the exponent to the denominator. Now, an example that we've seen before is the following. Let's say I had 2 times 3 raised to the third power. Is that equal to 2 to the third times 3 to the third? Well, since this is multiplication, And since an exponent tells us to multiply, every property every math operation that's taking place here is multiplication. So, do these two statements equal each other? Well, you can check that mathematically. Does 8 times 27 equal 6 to the third power? And if you do the math, you will find out that yes, that is. Right? Now the question is, what is the answer? So I'll remove the little question mark there. It is equal. What if there were addition? Does this concept still hold true? Well, we can easily figure this out by working out the numerical example. Order of operations tells us to do the following. Parentheses, exponent. While here, I do exponent and then addition. It is not true. Why is it not true? Well, the parentheses tells me add, multiply, while this is telling me multiply and then add. So those are not equivalent statements. One further example that I want to demonstrate with this power to a power rule is an example as follows. I have 2x to the fourth, y to the third, times 3x squared, y to the fifth, and all of that is raised to the second power. A natural inclination is for students to distribute this 2 to all 6 of the different bases here. And while that will work, and if you do everything correctly, will work, it is much simpler to simplify what's inside the parentheses by using our other rules, and then apply the power to a power rule. To the 6 of an exponent, and to the exponent of 8. Also, another common mistake. This 2 is an exponent. This means 6 squared, not 6 times 2 to get me 12. So you have to be careful with that. The fifth rule that I'm going to go through, which is pretty straightforward in terms of a rule, but sometimes a little bit difficult for students to get a hold of conceptually. I'll demonstrate as follows. We know from our quotient rule learned in the other video that 2 to the third divided by 2 to the third, I subtract the exponents when dividing, and I get 2 to the 0 power. Now that's nice, but what does 2 to the 0 power mean? Well, 2 to the third equals 8. 2 to the third equals 8. And we know that any number divided by itself is 1. Well, what have we just shown? Any number or any base to a 0 power is equal to 1. So, rule number 5, any base raised to the 0 power is equal to 1. So any base raised to the 0 power equals 1. There's really only one thing that you have to be careful about with this rule where students may make a mistake. And it's as follows. The question is, 2y to the 0 without parentheses, is that equivalent to 2y to the 0 with parentheses? Well, if you understand the rule properly, only y is being raised to the 0 power on the left side. So this is the equivalent of 2 times 1. While here, the entire statement of 2y is being raised to the 0 power, which means that is 1. Well, we clearly know that 2 does not equal 1. So these are not equivalent statements. And the point of it being that you have to be careful as to what is being raised to what power. If no parentheses exist, then that exponent only gets or applies to the base that it is immediately over. Now, I'm going to expand on this 0 exponent rule to demonstrate the following concept that hopefully will make sense when you see the examples I'm going to do. We know 2 to the 4th is 16. 2 to the 3rd is 8. 2 squared is 4. 2 to the 1st, excuse me, 2 to the 1st is 2. Excuse me. Now, if you can see the pattern that's happening here, I am subtracting 1 from the exponent. And here, I'm dividing by the base of 2. So following this pattern, you can see how 2 to the 0 power is 1. Well, now I want to continue this on to negative exponents. Well, what would happen? 2 to the negative 1 is 1 divided by 2, which is a half. 2 to the negative 2 is 1/2 divided by 1/2 by 2, which is 1/4. Continuing this over here, 2 to the negative 3 is 1/4 divided by 2, which is 1/8. And 2 to the negative 4 is 1/16. Hopefully you can see the pattern that my denominator is the same as what my numerator was when I had a positive exponent. So let me explain why that is working this way. If you had 2 squared over 2 to the 5th, your quotient rule told you to subtract these exponents, which would be 2 to the negative 3rd power. The problem is something like 2 to the negative 3rd power is really of no use to us because an exponent tells you to multiply a base a certain number of times. So conceptually, how do I multiply a base of 2 negative 3 times? It doesn't make any sense. So how do we deal with that? Well, we also learned, and did this in one of the earlier videos, that 2 squared are 2 2's, 2 to the 5th is 5 of them, and that we can mathematically simplify this by crossing out the common 2's in the numerator and denominator. When everything is crossed out, I'm left with 1 in my numerator and 2 to the 3rd power in my denominator. Well, now I could evaluate this because I know 2 to the 3rd power is 8. So, what did I just demonstrate for you? Well, the following. That any number or base to a negative exponent is 1 over that base with a positive exponent. Or in words, any base with a negative exponent can be rewritten as a base with a positive exponent by moving the base. Let me scroll this up a little bit more. From the numerator to the denominator or vice versa, which I'll demonstrate with an example in a moment. So, some examples with our negative exponents. If I had 4 to the negative second power, that's 1 over 4 squared, which is 1 over 16. If I had x to the negative fifth, y to the eighth, well, the y is okay because he has a positive exponent, while the x is not, so it needs to move. Now, when you recall our prior rules on dealing with the product or quotient or power to a power, the fact that I have negative exponents doesn't change any of those rules. So, for example, x to the negative 13th times x to the 5th. My product rule told me add the exponents. The only thing different is since I ended up with a negative, I've got to change it. Now, my quotient rule, if I had y to the 12th over y to the negative second, I could deal with this one of two ways. The quotient rule tells me to subtract. Well, that's 12 minus a negative 2, which students commonly make a mistake and write this as 12 minus 2, which is y to the 14th. Or, since y, sorry about that, on the 12, since y to the negative second is a negative exponent, I could move it to the numerator and get y to the 14th that way. So either of those two strategies work. It's just which one you are comfortable with. And then finally, my distributive rule still applies. If I have a to the 4th, b to the negative 3rd to the 5th power, I still distribute my exponent, a to the 20th, b to the negative 15th. But I don't like the negative exponent. I have to move the b. If you keep in mind that negative exponents do not mean negative numbers, but just mean that numbers will get small, that will help solve any problems you will have with understanding negative exponents.